All right, so in this video, we're going to prove the linearity of the integral. So it's the familiar, it's two familiar facts that if you integrate a constant multiple of a function, then it's the same thing as if you just integrate the original function and multiply by that constant. So constants factor out of integrals, the same way they factor out of sums, right? And the other thing is that if you add two functions, their integrals add. So, you know, sums can pass in or out of integrals. Sums commute with integration, if you will. So let's just state the theorem that kind of sums all this up. So this is theorem 33.3. So let f and g be integrable functions on AB and C any real number, then CF is integrable and the integral from A to B of CF equals C times the integral from A to B of F. And F plus G is integrable, and the integral from A to B of F plus G equals the integral from A to B of F plus the integral from A to B of G. Okay? So let's prove this. The proofs are conceptually, again, it's like they're relatively straightforward. There's just complication, you know, tedium introduced by the amount of notation and data involved in the actual integrals themselves. So okay, let's prove one. So clearly, it's true if C equals 0, because then CF is just 0 identically, right? So then basically the strategy here is, so let's suppose C is greater than 0. Okay, so this is kind of the simple, very straightforward case. So then for any partition P, on any interval tk minus 1, tk, we have that the sup of CF on tk minus 1, tk equals C times the sup of F on tk minus 1, tk. This isn't very hard to prove. So yeah, I mean, the book, I think, appeals to an exercise. Yeah. I'm going to skip over this too, because I think, I mean, hopefully by now, this is something that you can look at and kind of at least believe, and hopefully, you know, kind of in your head, some vague idea of how the proof might look starts to materialize. So yeah, I'm going to leave that. And the same thing is true for the inf. So from this, it follows that any upper sum of CF is just C times the upper sum of F for that partition. And the same thing is true for lower sums. Right? Because if you think about it, right, like the upper sum is just a sum of like these capital M's times tk minus tk minus 1. And so using this equation, you can replace each capital M of a CF with a C times capital M of F, right? But then you can just factor C out of the sum completely. So that's how you end up with C times U of FP. So this is pretty straightforward. And then from that point, right, so then, right, U of CF is the set of, or is the supremum, right, or sorry, the infimum of U of CFP, where P is a partition of AB. Oops. And so this is the infimum of the set of just C times U of FP, right? Oops, this is a colon where P is a partition, right? So in general, if, A is a subset of R and B is just CA for A in A. So this, well, yeah. Then sup of B equals C sup of A, and inf of B equals C inf of A when C is greater than 0. So if C is greater than 0, and right, that's only when C is greater than 0, because if C is less than 0, then it flips the orders of all the elements in the set, so that messes things up. But whenever C is greater than 0, it's not hard to prove that when you take a set and just like multiply every element by C, that multiplies the inf and the sup by C, right? And you can kind of visualize it on the real line. All that happens is you just scale the entire set, right? And it just shifts over. And yeah, so that's I think there's another exercise. They cited an exercise in here. I don't remember if I assigned it, but either way, it's pretty straightforward. So this basically means that U of CF, so U of CF is C U of F. And similarly, L of CF equals C L of F. And this is C times the integral from A to B of F. And this is also C times the integral from A to B of F. So that proves 1, right? Because these two are equal, so that means that CF is integrable. And of course, the common value here is the claimed value of C times the integral of F. So that finishes the proof of 1. It really is pretty straightforward. And then, so for 2, this is an elaborate epsilon over 2 argument, right? Whenever we have some kind of like operation, some analytical like structure or operation or something, property that we're talking about, and we apply it to the sum of two things, it's almost always some kind of epsilon over 2 argument in the end, like at heart. It's just that here it's more complicated because it's integrals. But yeah, you'll see. So actually, sorry, we haven't finished. So we only proved 1 for C greater than 0. So now suppose C equals -1. Then if you go through the so then right, so M of -f, basically go through the same process, you'll find something slightly different, equals negative little m of f tk minus 1 tk, and little m of -f tk minus 1 tk equals negative capital N of f tk minus 1 tk. So for any p, u of negative fp equals negative L of fp, and L of negative fp equals negative u of fp. So so u of f is the inf of negative L fp. Let's see. Yeah. Right. For the partition. Right. This is the negative supremum of the set of L of fp. P. Partition again, right? So that's negative L of f. Okay. And similarly, L of negative f equals negative u of f. So, well, right. So this is equal to negative integral from a to b of f. Since we assumed that f was integrable, right? L of f equals the integral of a from a to b of f. And then this one also equals negative integral from a to b of f. So negative f is integrable, and the integral from a to b of negative f equals negative the integral from a to b of f, right? So for any c less than 0, we can say the integral from a to b of cf equals the integral from a to b of negative cf, which is negative of the integral from a to b of negative cf, which is then negative of the negative c times the integral from a to b of f, which is c times the integral from a to b of f. So all we're doing is combining what we just proved, right? Because now this is greater than 0. So this is by what we just showed. And then this is by the case for c greater than 0, right? Because this is greater than 0. So anyway, that's that. Now that actually finishes the proof for constant multiplication. Okay. So now let's do the epsilon over 2 thing. So right, proof of 2. So what we're going to do is we're going to right. Well, okay. So given epsilon greater than 0, pick P1 and P2 partitions of AB such that U of FP1 minus L of FP1 is less than epsilon over 2, and U of GP2 minus L of GP2, oops, is less than epsilon over 2 as well. So then if we take P equals P1 union P2, right, because U of FP, right, U of FP will be smaller than U of FP1, and L of FP will be bigger than L of FP1. So the U of F and L of F U of FP and L of FP are closer than U of FP1 and L of FP1, right? Again, intuitively, this is just the idea that like when you add more points, the approximations get better. So the upper and lower sums have to get closer together, right? So then if, right, if we take P to be this, we have U of FP minus L of FP. This is also less than epsilon over 2. And U of GP minus L of GP is also less than epsilon over 2, right? So now, remember, well, okay, yeah. So now for any tk minus 1 tk subset of AB, we also know that the supremum of f of x plus g of x, well, yeah, basically, I'll just write it with the better notation. So m of f plus g, tk minus 1, tk, is less than or equal to m of f, tk minus 1, tk, plus m of g, tk minus 1, tk. Right, because if you think about it, basically what can happen, like if you think about if f and g like achieved maximum values, the biggest that the maximum of their sum could be would it be if the two maximum values occurred at like the same place, right, for the same value of x, and then they would add together to give the new maximum value of the sum function. But if the two maxima occur at different places and then they're smaller at other places, then they kind of like interfere with each other. So the maximum of the sum is actually not the sum of the two maxima, but it's smaller. But in any case, like the upper bound, the least upper bound of f plus g is less than or equal to the least upper bound of f plus the least upper bound of g on this interval, okay? For any interval. And these are for intervals in P, not P1 or P2, right? And similarly, L of f plus, so, well, okay, sorry. So that means that, U of f plus g p is less than or equal to U of f p plus U of g p, right? And similarly, L of f plus g p is greater than or equal to L of f p plus L of g p, right? So U of f plus g p minus L of f plus g p is less than or equal to U of fp plus U of gp minus L of fp plus L of gp, which is U of fp minus L of fp plus U of gp minus L of gp, which is in turn less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay, so this shows, so by 32.5 theorem, 32.5, f plus g is integrable, right? So then what we can say, right, we haven't said what the value is. So we just know that the sums of the upper and lower sums of f plus g for this partition P are within epsilon away from each other, but we haven't actually said that they are, close to, well, that the integral of f plus g equals the sum of the two integrals, right? So to do that, what we'll say is, okay, now the integral from a to b of f plus g equals U of f plus g, right? where this is just the upper integral. So this is like the inf, right? The inf of u of f plus g p, right? And this is because we showed that it's integrable, right? So we actually just showed this is true. So because it's integrable, this equality holds. And then this is less than or equal to, because this is the inf, so this is less than or equal to u of f plus g p, right? For the specific p that we chose, right? And then, so this is then less than or equal to u of fp plus u of gp by what we just argued, right? And then this is less than L of fp plus epsilon over 2 plus L of gp plus epsilon over 2, right? Because we showed that u of fp minus L of fp is less than epsilon over 2, right? So u of fp has to be less than L of fp plus epsilon over 2, right? So then this is less than or equal to, I'm going to combine the two epsilon over 2's, and then these are, L of fp is less than or equal to L of f, right? And this is, and then plus L of g plus epsilon, right? Which is the integral from a to b of f plus the integral from a to b of g plus epsilon, right? And then a mirrored version of this shows that the integral from a to b of f plus g is greater than or equal to the integral, or I guess greater, than the integral from a to b of f plus the integral from a to b of g minus epsilon, right? So right. So these two quantities are within epsilon from each other, but epsilon was arbitrary. So, so this absolute value equals 0, which means that the integral from a to b of f plus g equals the integral from a to b of f plus the integral from a to b of g. Okay. So that shows that the integral of the sum of two functions is, that the integral splits across the sum, like this. And in total, these two things combined are what we call linearity for the integral. Okay. So great. In the next video, we'll show a couple basic facts about like inequalities of integrals. Yeah, which are just really useful when doing like estimates and various other analysis-y arguments with integrals.